So last time we ended with simplifying rational expressions. We talked about multiplying, um, and a lot of that just entailed knowing how to factor and canceling the common factors. And then we talked about dividing rational expressions. It really just boiled down to doing keep, change, and flip, and applying the same procedure that we did for multiplying rational expressions, which is, again, knowing how to factor. And that's an extremely important skill to know. Alexander has asked, do you know any problems, good resources for problems, extra practice? And that's a great question. Well, the textbook, the textbook that comes with it, Precalculus, they have pretty good extensive number of extra problems at the end of each chapter. If that doesn't suffice for you, Alexander, I can personally give you more. You just have to specify exactly what topics you want to really work on. So that's an excellent question, because it shows me that you are interested in learning, and a lot of these problems, right, require a consistent amount of and a substantial amount of practice. There's no way around it. Sometimes it's not just enough by looking at how the professor or the teacher or the instructor solves a problem. It's not enough. You yourself have to go through it. It's like building experience, right? You can't transfer experience from one person to the other. You yourself have to go through them. So yes, I would be happy to just give you problems to do, because I really think that's the best way to learn. You learn mathematics by doing it, not by watching it. Okay. Now let's continue with rational expressions, and now we're going to talk about adding and subtracting, which are the more difficult operations to apply when compared to multiplying and dividing them. This is a particular topic where many students have a little bit more issues or a little more trouble with, because it's a little different from multiplying and dividing. Okay, so this is lecture number 3. Today is the 8th. Okay, we're going to have a little bit more review here. And we're going to continue with this whole, so we were doing simplifying, right? We were simplifying rational expressions. We simplified a whole bunch of radical expressions, and we've talked about exponential expressions, and we talked about compound complex fractions. So we've done a lot of simplifying so far, which is good. Okay, so this is 4 continued, and this is on simplifying. Rational expressions. And this is going to be an example on adding. Now I'm going to have 2 rational expressions, and I'm going to ask, how do you add them? So for example, if I have 3 minus x over x squared plus 7x plus 12, and if I add that to x minus 5 all over x plus 4. So how do we proceed? What's the first step? Does anybody remember? So I should maybe specify our goal is to, again, we want to factor. And our goal, what's our goal here? our goal for adding is to rewrite as a single fraction. So that's our goal. I want to make these two fractions and put them together into one single fraction. So Rita says, hey, let's factor. Let's factor. So let's look at the first expression. These expressions here are only binomials. You can't really factor them any further. So the only expression here that you can factor is this denominator. So what's the factorization of x squared plus 7x plus 4? This plus 12. I don't know why I said 4. What is this quadratic expression factor into?
X plus 4 and x plus 3.
Correct. Thank you. So this is x plus 4 and x plus 3. Okay, great. So we were able to factor so I would say step 1 is to factor, if possible, all of the denominators. So we don't really care so much in terms of factoring the numerators. We just factor the denominators. Oh, Chen raises a great question. How do you decide when to use the AC method or just do the x plus number times x minus a number? Very simply. So the AC method, the AC method can be applied for any general quadratic. It is just that it is easier to not use the AC method whenever the quadratic has a single 1 in front of the coefficient as a coefficient for x squared. So when your x squared term has a 1 or you just see one x squared term, then you only need to do that little process where we find two numbers that multiply to 12 and then add to 7. You can still do the same AC method. You can still say, and if you think about it, you really are doing the AC method. You're saying 1 times 12, which is just 12. What two numbers multiply to 12? 3 and 4. What two numbers add to 7? 3 and 4. So you're still doing the same exact thing. It's just that we already know what the result will be because of this very nice 1 that's in front. So that's why we just do x plus 4, x plus 3, because we already know. But if this number was, for example, a 2 or a 7, then we do the AC method. Okay? But great question. Good. So if possible, factor all the denominators. That's step number 1, and we did step number 1. And I just rewrote it when I should have factored. So this should be x plus 4, x plus 3. Okay, good. So now we factored everything that we possibly could. Now, what is the second step? So to figure out the second step, you have to try to go back and think about, how do you add fractions again? What is the prerequisite?
Finding the
What
common
is the
denominator.
requirement? Right. I need to have the common denominator. So the issue is I don't have a common denominator. So I need to make, so what we need to do is find what's called the LCD, which is the least common denominator. They need to have the same denominators. So if you now you have to look at the denominators, x plus 4, x plus 3, that's one denominator, and then have an x plus 4 as a second denominator. So what would be the LCD for this particular problem? This is the hardest part, I believe. So x plus 3, not exactly, x plus 4, not exactly. Okay, so look at this portion here. If I do 1/3 plus 1/5, right? Let's go back to, middle school. And when we add these, how do we add these? We need to find the least common denominator, correct? And what would be a least common denominator between 3 and 5? 15. Oh,
15.
right, 15. But where does that 15 come from? It comes from 3 multiplied by 5. So essentially what we're saying is, hey, I want to make both of these the same. But in order to make both of these denominators the same, I need to include the factor that's missing. So 3 here is there, but 5 is not. So that's why we do what? That's why we do this whole multiply by 5 thing on this fraction. And then this denominator has a 5, but not a 3, because I want to make them the same. So then what do? I multiply both sides of the fraction by 3. And then I get what? 5 over 15 plus 3 over 15. That equals 8 over 15. So that's one way to approach this. We want to make them the same. And how do we do that? We multiply the exponents, right? I mean the denominators. That's one way. So in this scenario here, the LCD here, if you notice, the x plus 4 is in both of these. So that's definitely part of the LCD. Definitely. X plus 4. Now the issue is this x plus 3 only exists in this denominator, but not in this denominator. So then we start to see that, oh, I am missing. The denominator here is missing the x plus 3, which makes the x plus 4 times x plus 3, it makes it the LCD. So this first fraction already has the LCD underneath. So I don't have to do anything to that fraction. I only have to do it to the second rational expression. So this rational expression here just goes along for the ride for now. And then I do plus x minus 5 over x plus 4. And I'm going to multiply the top and the bottom by the missing factor, which is x plus 3. Now, some people may be tempted to be like, oh, x plus 3 cancel out. No, we can't. We're not going to. But why not? Well, the reason why is because then it undoes what we're trying to do. It's going like we go back to square one. We're not trying to do that. That's why this problem here is a little different from multiplying or dividing rational expressions, because we're not doing the same thing. So again, this is x plus 4, x plus 3. And now at the top here, the bottom, I'm just going to write x plus 4, x plus 3. And the top here, I'm gonna actually distribute everything. So I'm going to distribute the x and FOIL, right? I'm going to FOIL. So x times x is x squared. X times 3 is 3x minus 5x minus 15. And then I get 3 minus x all over x plus 4, x plus 3, plus x squared minus 2x minus 15 all over x plus 4 and x plus 3. So do you see how we did that? It looks more complicated than what we started, but actually it's better because we have the same denominators. So then this is step number 2. Step 3 is to multiply the numerator and denominator by the same, or by the quote unquote missing factor of the LCD for each rational expression, quote unquote missing. So that's step number 3, and this step number 3 is right here. And then step number 4 here, we, if needed, step number 4, if needed, multiply the numerators by missing factor. So this is step number 3, and then step number 4 is right here. Okay, and then we continue. So look what we did, guys. We have the same denominator. Check. So if we have the same denominator, what can we do now? Was the LCD x plus 4, x plus 3? Yes, that is the LCD, Alexander. And then x plus 4 as a numerator. I don't know about the x plus 4 as a numerator. I'm not sure about that question. All we did was we found the LCD among the denominators. We recognized that this fraction already has the LCD, so I don't really have to change this. I only have to change the fraction that that doesn't have the LCD. So I am missing the x plus 3 for this fraction, right? And then I multiply the top and the bottom by that missing fraction, and then I multiplied these numerators out, and then I combine like terms, and now I have the same denominator. And I think Judy said correctly. Now, since we have the same denominator, we can keep the denominator and just add the numerators, which is exactly what we wanted to do, right? We wanted to keep this into, we want to rewrite this as a single fraction. So then step 5 is you combine the numerators, combine numerators under a single denominator, under the single denominator. In this case, it's the LCD. And then I can combine like terms. So this is step number 5. And then when I combine like terms, I'm left with x squared minus 3x minus 12 all over x plus 4, x plus 3. So awesome. Look what we've done. We went from having two fractions that are being added to one another to now having a single fraction. So our goal is completed. However, we always want to see if it's possible to further simplify the expression. So at this point, we want to see, hey, if possible, step 6, if possible, factor to simplify the rational expression. So the nice thing is that the denominator is already factored. So we have to look at the numerator. Like, so again, the question is, can I find two numbers that multiply to negative 12, but when you add them, give me negative 3? Are there any two numbers that multiply to negative 12, but add to negative 3? So 1 and 12, 2 and 6, 3 and 4. So it looks like you can't, right? There is no two numbers that multiply to negative 12, but that add to negative 3. So if that's the case, we just leave it. There is nothing we can do. So this is the final result. Okay. Make sense? Okay, so that's adding, and subtracting is pretty much the same way, same procedure. It's just that instead of adding, when it comes to step number 5, instead of adding them, we're going to subtract. And then we had to just pay very, very careful attention when you subtract the numerators, because you're subtracting the entire second numerator. And many students forget to distribute that negative sign. So we'll do one of those, and then we'll be done with rational expressions. So here,
Professor,
yes.
if you would have, before you did the last step, if you would have just changed the left side, like where it's 3 minus x, if you would have just made that negative, could you have just like canceled out like terms after that and made turn it into like x plus 3 and that whole like part just a negative, and just could you have simplified it from there?
So you're talking about this moment here,
Like right
or
before
the
that.
here.
Yeah, and just turn that whole left side where it's 3 minus x, that part of the equation, just all of that negative, and then turn that into x plus 3, and then the right side you could have made it x minus 5x plus 3.
I don't see the need for that. So you're saying
And if,
make this
now I'm
an
wondering if you could like simplify it more from that, because they have yeah, I was just wondering.
oh,
I
I
remember
see.
doing it like I
I
don't remember
see what
for what, but
I see what you're saying. You're saying that, can I make this like I know what you're talking about. You're talking about, I'll show you what you're talking about. But you're talking about like, oh, let's make this positive,
yeah.
right? And then cancel that with the x plus 3 like that.
Yeah, and then on the other side you could also cancel the two x plus 3's, and then it just be negative 1 x plus 4 x plus 3, and then x minus 5 over x plus 4. That wouldn't
Yeah.
work.
No, that wouldn't work for this, but I know what you're talking about. You're talking about like something like this. But the thing is, if you notice, you wouldn't be able to cancel the way you think. Um, you're talking about this when you have something like x minus 3 and you have 3 minus x, right? You would say, oh, this is negative parentheses x minus 3 over x minus 3. Cancel these out and you get a negative 1.
No, I'm
Right?
saying make the whole like that whole side, like put a parenthesis around that whole like side of the equation over the 3 minus x over x plus 4
Like this.
x plus 3. Yeah, like that.
Yeah, but so the moment you start putting negatives like this, you're just changing the entire problem.
Okay.
Yeah. So in this problem, you don't need to do that. You just straight up say, take this, and combine, and move on. That's why this takes a little bit more practice, because it's similar to the other things you do with multiplying and dividing. But in this particular problem, we don't want to cancel anything until the end. Like with the multiplication of rational expressions, we want to get stuff out of here as quickly as possible. Like the moment we start factoring, boom, we just cancel things out, right? And then we're happy. It's just
Mhm.
that when we talk about adding, which you're thinking, wait, adding is easier than multiplying. Actually, adding rational expressions takes a bit more, because we're trying to rewrite our expressions with the same denominator. And that takes some understanding of what the LCD is. Then after that, we're not going to cancel anything. Even if this was, listen, even if this was a 3 plus x, so you would be tempted to be like, oh, let me cancel the, no, leave it. Leave it. Combine the numerators first. That's why we have this step procedure here. Combine the numerators first, and then at the end, factor, cancel, simplify. It's just the nature of adding and subtracting rational expressions. It just comes with the territory. So I know you want to just cancel stuff out in the middle, but no, we're gonna leave that till the end. Okay. I hope that makes sense. So we'll do another example with subtracting this time, and then we'll see if that makes things a little bit more understood.
Okay.
Okay, so let's let me get an example for subtracting. Subtracting. Okay, so suppose I get something like this. X over x minus 4, and then I get a minus 3 over x plus 6. So you see here, I want to subtract. And again, the goal of subtracting rational expressions, the goal is to combine two fractions, or combine the rational expressions into a single simplified fraction. That's the main goal. That's the overarching goal that we're trying to do. Right now, we have two separate fractions and we're saying subtract them. And again, I'm not going to rewrite this. It's literally the same thing. So factor if possible all denominators. Well, I can't do that because all the denominators are already simplified as much as possible since they're all binomials. Okay, step 2 says find the LCD. So that's the most important step here, the LCD. So what is the LCD among these two fractions or rational expressions? And again, this is like the key here. If you don't have the LCD, you don't have anything. You can't start. Right, so that's right, Tiffany. So in this problem, it's very simple, straightforward. When you have two just different fractions underneath, then the LCD is literally just multiplying them both. So the LCD here would be x minus 4 and x plus 6. And then step 3 would say multiply the fractions with the missing factor that they have. So x minus 4 does not have the x plus 6, and the x plus 6 does not have the x minus 4. So we're going to multiply accordingly by the missing factor. So I'm going to multiply this by the x plus 6 over the x plus 6. Again, I'm not going to cancel anything. Even if they were the same, I'm not going to cancel nothing. And then this one here, well, there's a minus. So be careful with that minus sign. And this would be x plus 6. And I'm multiplying the top and the bottom by x minus 4, x minus 4. So the denominators, I'm just going to leave it as a multiplication of the x plus 6 parentheses x minus 4, because that's how you multiply fractions, right? You multiply by just multiplying across. So I multiply x plus 6, x minus 4, but I'm not going to foil. I'm not going to foil. And in the bottom here also, this will be x plus 6, x plus 6, x minus 4. I'm not going to foil because I may simplify at the end. So I'm just going to leave it as simplified as possible. But the numerators, I am going to expand. I am going to distribute. So I'm going to multiply x plus 6 with x. So I'm just going to make that explicit here. X plus 6 times x. This would be 3 multiplied by x minus 4. So again, you see here, you would be tempted. Oh, let me just divide the x plus 6s and x minus 4s. But if I do that, I get back to square one. I don't want to go back. I want to go forward. So hold on your horses with the whole simplifying thing for now, and you'll see why we don't do it yet. So x times x is x squared plus 6x. So that's going to be the numerator on top here. Again, I'm going to leave the denominator in with the LCD just the way it would be. This would be 3x minus 4, minus 12, because I distribute. And this would be x plus 6, x minus 4. So this is what we have so far. Now, the key step here that I would like just to highlight is that I'm going to subtract this second polynomial. So be careful when you do so. And just to keep that in mind, I'm going to put parentheses around. I'm gonna put parentheses. I'm gonna change this color here just to emphasize that. So I'm gonna put parentheses around the second fraction here, the second numerator, just to make sure we remember that we're going to distribute this -1 here. We're distributing the negative sign. So in reality, what we have is x squared plus 6x minus 3x plus 12 over x plus 6, x plus 6 and x minus 4. Okay, and this becomes x squared plus 3x plus 12 all over x plus 6, x minus 4. Okay. Why is it multiplied by -1? Well, what we're doing is we're saying, right, we're doing this. We're saying 5 minus x plus 3, for example. I'm doing 5 minus x plus 3. It's the same thing as saying 5 times -1 of x plus 3. It's like saying when you subtract, it's like saying you're multiplying that thing that you're subtracting, you're multiplying it by -1. It's equivalent. So when we're saying x squared plus 6x minus parentheses 3x minus 12, we're essentially saying multiply this by -1 and then combine. I know it's a little strange to hear this, but subtraction is really just addition of what's called the additive inverse. It's a fancy way of just saying you're just taking what you're like. In other words, you can do this. You can say 5 minus 3, right? You can rewrite this as 5 plus -1 times 3. I know it sounds like that sounds more complicated than it is, but that's one way to interpret subtracting. You're really adding the multiplicative inverse of the additive inverse of 3, which is just saying multiply by -1. So that's where the -1 comes into play. And so we have our final rational expression as a single fraction. And we want to see if we can. If not, then just leave it. Can we combine? Can we factor the numerator and further simplify? And again, we get a polynomial, a quadratic here that's not factorable. So we just leave it. We just leave it. So these two examples didn't have the simplification at the end, but that's okay. But the idea is knowing how to combine the two fractions together. All right. So that's simplifying rational expressions. We've talked a lot about simplifying thus far. We talked about factoring. Awesome. And now I would like to talk about solving. So we're done with this whole segment here of simplifying. So now that we have that under our belt, we're going to talk about solving equations. In particular, we're going to be talking about solving quadratics. So solving quadratic equations. And I have a feeling that many of you know. So no, this is still a review, Alexander. I just want to make sure we have all that we need for what's to come. So solving quadratics. I'm pretty sure most of you know how to do so. So I'll give you a particular example here. So what if I have something like this? What if I have 5x squared equals 10x? How do you how do you solve this? I want to solve.
We can start
Solve for
by.
x. Mm-hmm.
Sorry.
Go ahead.
Do we subtract 10x and like make the equation equal to 0?
Correct. So that's step number one. Very good. Step number one is set equation equal to 0. Always. That's what we're going to do every single time we have a quadratic equation. So this is for solving quadratics, right? So we're going to subtract 10x on both sides. And then I get 5x squared minus 10x. This equals 0. Okay, so I set it equal to 0. Great. Step one is done. Now what?
Factor out the GCF.
Very good. Very good. So if possible, factor the trinomial, factor the quadratic expression. Good. Now, do you see how these skills that we've talked about, simplifying and factoring, they're embedded in almost everything that we do. So factoring, you have to know the factorization techniques. So in this problem, the only thing we could do is factor out the GCF. So then I can factor out the 5 and the x. And I'm left with x minus 2. Great, I did it. Step number 2. I factored the 5x. That's the only thing that's in common. Okay, and now what? So I have the factorization. And then what's the next step? We're almost there. We're like right there.
Now we solve for x, or
Mhm.
we have two equations.
Right. Right. So that property, I mean, it's called, people call it this apply the zero product property. Apply the zero product property, which just states the following. If A times B equals 0, then either A equals 0 or B equals 0 or A and B equals 0. So that's the whole idea. So if I have a product, right, and that product gives me 0, that means that either the first product, the first expression for the product, either that equals 0 or this second would equal 0. One of them has to equal 0. And then I can solve, right? Then solve for x. Step 4, solve for x. So then I get x equals 0 and x equals 2. And then we write our solution. We can write it as a set. So x is equal to, the curly braces is for a set, 0, 2. So my x values that are in the set of 0, 2 is the solution to the original quadratic equation. Okay. So nothing out of this world. Again, things that we've seen before. I hope. Okay, what if I get something like this? Solve for x. Solve for values of x. Yeah, solve for all real values of x. So what if I get x multiplied, let me just write it like this. X multiplied by x minus 2 equals -1. we do here? Set it equal to 0. That's right. So I'm going to set it equal to 0. First, I need to do what? I need to distribute. Then I get x squared minus 2x equals -1. And then I'm going to add 1 on both sides here. So then I get x squared minus 2x plus 1 equals 0. Very good. So that's step 1, right? That's my step 1. I set it equal to 0. Then what? Step 2 would be to factor. Very good. Can we factor this? Is this factorable? X squared minus 2x plus 1. Yeah, we can factor it. So what is the factor? What does this factor into? Yeah, x minus 1 times x minus 1. So this can be written as x minus 1 times x minus 1. This equals 0. So if that's the case, I can also rewrite this as x minus 1 parentheses squared because I am multiplying it to itself, right? And then x minus 1 squared equals 0. That's only possible if x minus 1 equals 0. That's the only possibility. And if x minus 1 equals 0, then x equals 1. So my solution is only a single. So you can write it this way. Maybe that's not necessary. You can just write x equals 1 as my solution because I only have one x value. That's the solution. Okay. See, Natalia, yes. If you have a question. Excellent question. That is exactly what I'm going to do next. Of course. So let me just say, the quadratic formula is bulletproof, meaning that it always works. So I'm going to give you the next example will be one where factoring is not possible. So then maybe the question should be, why do we factor? Why don't we just use the quadratic formula every time? You can be my guest. If the quadratic formula is something you love to use, be my guest. But there's some problems such as this one where the quadratic formula is just, for me, in my opinion, a little too much, right? Because we have to apply the whole plugging in. Whereas if you factoring is better, easier to deal with because we're breaking up our expression into little pieces that it's easier to solve. But again, this is very preferential. It's not saying, oh, if you apply the quadratic formula here, then no, it's bad. No, you can do it. Be my guest, like I said. But if you can factor, I would recommend, highly recommend factoring because factoring is nice. It's just quick. You see how quick we did this? Imagine trying to apply the quadratic formula for this. Not that it's impossible, it's just more work, but it always works. So we'll see what happens here. So in this third example here, I'm gonna have something x squared plus 8x minus 4 equals 0. So in this problem here, I already have it set it equal to 0. I want to solve. Then the first thing would be, hey, can I factor this? Can I find two numbers that multiply to -4, but that adds to 8? And of course, there is no two factors. There are no two factors of 4 whose sum give me +8. The factors of 4 are smaller, so there's no way to get to 8. So then the question is, oh, we can't factor. So let me just note this. This is not factorable, but don't fret. That's okay. If it's not factorable, we're going to use something that always works. Use the famous or infamous quadratic formula. Again, this always works. So the quadratic formula is what? Does anybody remember the quadratic formula? Recently, I heard there's like the song for it. I did not learn it with the song, but does anybody know the quadratic formula?
Is it negative b plus or minus the square root
Uh-huh.
of, what is it?
So,
B
so
squared minus 4AC.
thank you. Thank you for
Over
helping. Over
2A.
all over 2a. So this is the handy dandy quadratic formula. Okay. And this expression underneath the radical is known as the discriminant. And that tells you what kind of roots you'll have. But don't worry about that for now. And these A's, B's, and C's, what do those represent? Like, where does that come from? What is the A, B, and C?
Like the B is 8 and A would be the 1, like which is not present there, but and 4 would be C.
-4 would be C. So just keep in mind that this formula comes from the general. This comes from the general quadratic equation. And what is the general quadratic equation? It's ax squared plus bx plus c equals 0. So that's where it comes from. So a represents the coefficient of x squared. B represents the coefficient of the term x, and C represents the constant. So what is our A, B, and C? Well, you just said it. I don't know your name. I don't know who said it, but someone said it. A is 1, B is 8, and C is -4. Right? Was that Sanjana? Was that you?
Yeah, it was me.
Okay. Pop goes the weasel, huh? That's how it goes. Negative. I don't even know how to make that song. But anyways, good. So we know A equals 1, B equals 8, and C equals -4. Now all we do is plug in. So plug in the values. Plug in values into the quadratic formula. Okay, so this will be x is equal to, this is -8 plus or minus the square root of 8 squared minus 4 times 1 times -4 all over 2 times 1. So all we did was I plugged in everything, right? In its respective place. This is -8 plus or minus the square root of 16 plus 16 over 2. 16 plus 16 is 32. So this is -8 plus or minus the square root of 32 all over 2. And then we ask ourselves, hey, could we break down the square root of 32, right? Oh my goodness, you're right, guys. You're right. This is not 16. It's a 64. That's my mistake. So 64 plus 16. What is 64 plus 16? 80, right? Okay, good. Yeah, pardon me for that. Thank you guys. See, you guys are better than I am. Look at that. So then square root of 80, can we break down, can we simplify? Square root of 80? Remember we talked about simplifying radicals a lecture ago. 10 and 8. Remember, when we simplify, we want to find what are the largest factors that are perfect squares. So what's the largest perfect square? Yes, that's right, Felipe. 16 and 5. So square root of 16 times the square root of 5. We could have done 4 and 20, Sydney, but then we would have to break down 20 afterwards. So might as well get the largest perfect square that's a factor of 80. In this case, it's 16, and then it becomes 4 times rad 5. So then I can replace this with -8 plus or minus 4 square root of 5 divided by 2. And then what's nice is that both 8 and 4 is divisible by 2. So what I could do is I can simplify this by taking -8 divided by 2, and I can split up the fraction 4 rad 5 over 2. And then I can cancel the 2 and the 8. This becomes a 4. The 2 and the 4, this becomes a 2. And then finally, my answer is x is equal to -4 plus or minus 2 rad 5. And I just want to write the solution a bit more explicitly. So I'm going to write it as a set where the first one is -4 plus 2 rad 5, and the other one is -4 minus 2 rad 5. And of course, this is the exact value, right? The exact value for x would be -4 plus 2 rad 5. That's one of them, right? And if you want the approximate value, you would put that in your calculator, and your calculator will give you a decimal representation. So let me find that myself. So -4 plus 2 rad 5. So if you find it yourselves on your own calculator, I believe you'd get 0.472135 dot dot dot. This goes on forever. This is an irrational number. Okay. So the exact value just means that it's not approximated. It's exactly what it is. Rad 5 is rad 5. But if you want to find the decimal expansion, then you would have an approximated value. And of course, your calculator only gives you several decimal values. It doesn't give you all of them because it's an infinite number. Okay. So are we good with solving quadratics? Yes. We've seen this before, right? We've touched upon it. You guys touched upon it before. Okay. Awesome. All right. So we're gonna stick around with quadratics, but in particular, we're not gonna talk about quadratic equations. That's something that you've definitely seen. Most of you have seen. And we're gonna touch upon something a little different, a little new, maybe for most of you. And this is what's called solving quadratic inequalities. So now we're going to be talking about quadratic inequalities for a tiny, not a tiny bit, but for a bit. Okay? It's quadratic inequalities, yeah. So in this case, we're not going to use the quadratic formula because the quadratic formula only is applied for equations, not inequalities. So let me give you one example. So I want to solve the inequality. Solve the inequality. And this inequality is this: x squared less than or equal to 5x minus 6. So you see here we have a less than or equal to symbol, not an equal sign. It's a less than or equal to symbol. So how do we go about doing this? Well, step one is pretty much the same as the previous steps that we've done. Is set inequality with 0 on one side of it. It's pretty much the same thing, right? We want to put everything on one side and everything and leave the other side a 0. So we can subtract a 5x on both sides, and we can add the 6 on both sides. And when we do so, these cancel, leaving nothing, leaving 0. And I'm left with x squared minus 5x plus 6. And now, step number 2. I want to see, if possible, factor. And I believe for most of these problems, they're going to be factorable. So if possible, factor. So can we factor x squared minus 5x plus 6? Chen, we can definitely subtract x squared. We can definitely do that. It's just that when we do that, it causes more, it may cause more confusion with the symbol, with the less than symbol. And then we have to take care of that negative x squared and then make that negative x squared into a positive one. So I'd rather not do that and just move everything, keep the x squared the way it is and just move everything on the left side. It's just a bit easier to deal with, I believe. But yeah, you can definitely subtract x squared. That doesn't matter. It's just that if you know what you're doing, then okay. From here, I think some of you guys said x minus 3, x minus 2, which is right. Perfect. Awesome. And then it says that we can get negative 3, negative 2. Now at this point, okay, at this point, this is where things get a little different from what we've been normally accustomed to solving quadratic equations. From this point, we're going to use a number line. We're going to use a number line and divide the number line into sections using the roots of the quadratic. So let me just say that the roots is just another way. So note, roots is equal to the solutions, which is equal to the x-intercepts. So whenever you hear the word roots, it's the same thing as saying the solutions. It's the same thing as saying the x-intercepts of the quadratic. So what would be the solution to this quadratic if this was just an equation? You would do what? You would do the x equals 3, right? And x equals 2. So x equals 3 and x equals 2 would be my solutions if this were an equation. But because it's an inequality, we're treating this a bit differently. So we're going to do this. We're going to say, hey, number line, I'm going to split it up into sections using the roots. Do you see that? So 2 and 3 are the roots. The roots or the solutions, roots of quadratic. Does everybody follow me? Now, what we're going to do is we're going to select what are called test points. So step number 4 is use test points from each interval. So maybe I should, these sections are going to be called intervals. Right? When you divide up the number line, you get an interval, right? So now I'm going to select not randomly, but I can select. I have 3 intervals when I divide it using the roots of the quadratic. And now I'm going to select a number within those intervals. And I could choose any number within those intervals. But of course, some numbers are just more convenient than others. So for example, what's a number below 2? Smaller than 2, that's easier to use. And those will be my test points. So a number smaller than 2 would be 1, right? Perfect. So 1. And then what's a number between 2 and 3 that's easier to use? 2.5. Okay. See, you start to get the hang of it. And what's a number bigger than 3? 4. Okay, so I'm going to use these numbers. So these are my test points. So step number 4, test points. And how am I going to use the test points? I'm going to plug it into the quadratic expression. So use test points from each interval. Sorry, I should write this. And plug in the quadratic expression. Can't spell expression. Expression. And let me just highlight that this is the quadratic expression. Okay, so then test point number 1. So test points. So I got x equals 1, I got x equals 2.5, and I got x equals 4. So I'm going to plug it in. What's 1 squared minus 5 times 1 plus 6? I get 1 minus 5 plus 6. I get negative 4 plus 6, and I get what? A 2. Now you guys are like, wait, why do I care about what the quadratic is? Well, I'm trying to look for which one of these intervals include the x values that satisfy my inequality. So my inequality originally, look what it says. It says that the quadratic, whatever the quadratic is, must be less than or equal to 0. Well, I plugged in a number from this that comes from this interval, and I realized that my number at the end is a 2. Is this smaller or bigger than 0? It's bigger. It's not smaller, right? So does this satisfy? Does x equal 1? Does this satisfy the inequality? Meaning, does it make it true? No, right? So we're saying, hey, this is bigger than 0. So this is no good. So what do? We in a way we can just say, hey, this inequality is no good. Then plug in 2.5. So using a calculator here might be very useful. 2.5 plus 6, because you don't have to worry about all these calculations. So negative 2.5 squared, then it will be minus 5 times 2.5 plus 6. So then when I put this in my calculator, the result is negative 0.25. Negative 0.25 is smaller. It's smaller than 0, which is good because that's what I want. I want smaller than 0. So then what do I say? This interval in between is good. I could choose any number between 2 and 3 and it will produce the same result, something less than 0. And then finally, just to make sure the last interval, whether or not that's a good or part of the solution, I'm just going to plug in 4. 4 squared minus 5 times 4 plus 6. I get 16 minus 20 plus 6, I get -4 plus 6, and I get something that is bigger than 0 again. So that means that this inequality, this interval, pardon me, is no good. So what is the appropriate interval? Where's everything between 2 and 3? Now the question becomes, do we include the interval points, the endpoints of this interval in this problem? Do we include them, yes or no? That's right, Sanjana, we do. Why do we include them? Right, because of the equal sign, right? These 2 and 3 are exactly the x values that make it equal to 0. They're the ones. That's how we started it, right? We started with using the roots. The roots are exactly the x values that make my equation, quadratic expression, equal to 0. So we're still going to include them as well. So then what would be the final solution to the inequality? So my solution to the inequality, to the quadratic, to the quadratic, oh my goodness, I can't even write, to the quadratic inequality. So how would we write this? So this is the graphical version of it. We can write it as an interval notation. We can also write it as set builder notation, and I'll give you both. But the more common one that we're going to use is the interval notation. So the interval notation is really straightforward. So the interval that I have is from 2 to 3, and I include 2 and 3. And because I include 2 and 3, I need to use the square brackets here. And that's my interval. The set builder notation would be all x values such that x is less than or equal to 3 or greater than or equal to 2. Again, these are the same things, just that they're written in different notation. Does that make sense? Has anyone seen this before? Is this completely new? No? Yeah, this is something that is not so commonly taught, but some people have seen it before. Okay, great. Good. Good. Okay, so that's how you solve inequalities. I can give you one more example. Let's do one more, just to see it again. Let's see. What if? Yeah, I'm gonna give you not a quadratic inequality. What if the 2, 3 wasn't included? How would you write the interval notation? Well, then that becomes a bit more complicated, right? Then we would have to find the roots regardless. We have to find the roots of this quadratic. You have to start with the roots. That's all. Once you have the roots, then you can divide up the interval. Then you can know what numbers to choose. Then you would know what would be the intervals. So we got the 2 and the 3 because they are the roots of the quadratic. That's why. That's how we got it. So if this quadratic was something else and did not have 3 and 2 as the roots, it would have some other kind of root. So let's see. So for example, what if I had something like x squared minus 2x minus 2x, pardon me, minus 7x minus 7x, and then it's greater than negative 10. Chen, yes, any number between 2 and 3 to test it, you can choose anything. 2.1, you can use 2.9, you can use any number. So what if I have this one here? So the step would be what? Right, we want to set it equal to 0. So we're gonna add 10 on both sides. And then I get greater than 0. I get x squared minus 7x plus 10. So we set the inequality on one side of it being 0. Then we can factor. And what does this factor into? Negative 5 and 2. So this becomes x minus 5, parentheses, x minus 2, greater than 0. And so then we know that the root's going to be what? What are the roots? So x equals 5 and x equals 2, right? Those would be the roots. Oops. And then I can do the number line. And then I can split up the number line into these roots 2 and 5. Then I would have to choose numbers in between these roots, these intervals that are simple to use. So a number less than 2 that's easy to use could be 1. Even easier than that, I would say is 0. 0 is an easy number to use. Between 2 and 5, we can choose 3. And bigger than 5, we can choose 6. But again, we can choose any number as long as it's in those intervals. So these are my test points. So I have the first one is x equals 0. The second one is x equals 3. And the last one is x equals 6. And again, I'm only going to plug in to I'm plugging these x values into the quadratic expression. The quadratic expression here is x squared minus 7x plus 10. And actually, what would be easier to do, well, we can just do it for this one. So when I plug it in, I get 0 squared minus 7 times 0 plus 10, which is just what? 10, right? This is bigger than 0. So what does that mean? That interval is good. Between 2 and 5, I'm plugging 3. And what I was going to say is that instead of plugging in like this, 3 squared minus 7 times 3 plus 10, like instead of doing that and then squaring the 3, multiplying the 7 and the 3, and then adding the 10, instead of doing that, it's easier to leave it as the factored form of the expression. So it's easier to do this. 3 minus 5 and 3 minus 2, isn't it? Isn't it easier to do this expression here than to do this expression? It's less work. 3 minus 5 is negative 2. 3 minus 2 is 1. Negative 2 times 1 is negative 2. Negative 2 is less than 0, but we want something bigger than 0. So, big X. And then finally, 6. And like I said, I can do this, right? 6 squared minus 7 times 6 plus 10. But that's equivalent to saying 6 minus 5, 6 minus 2. Do you guys see that? Do you guys see how it's easier to use the factored form rather than the actual quadratic expression? Because the computation is easier. So 6 minus 5, as you can tell, is just 1. 6 minus 2 is 4. 4 is bigger than 0. So therefore, we say what? Good. So then what would be the interval? What would be my solution? Anybody? Does anybody? So no, Sanjana, it would not be 2 comma 5 because 2 to 5, we're saying that this interval is no good. So we're using the intervals on the outside. And Sydney, it's not 2 to negative infinity because the 2 is not included. And the negative infinity is to the left of 2. So that should be written first. So this interval here is negative infinity, because I'm using all of this, not just 0. I'm using all of this. So negative infinity all the way to 2. And I'm not using the 2. I'm not using the 2 because remember the 2 and the 5 come from the fact that this expression equals 0. But the inequality is just strictly greater than. So we don't include a 2. So then we say 5 to infinity. And what we do with this, we normally put this U symbol inside. This U symbol represents what's called the union. It's the union. So you're just putting them in a way saying that it's negative infinity to 2, including 5 and infinity. And so then this would be the final answer. So how are we feeling about this? Good? The inequality is just including test points, and now we're using interval notation to express our solution. Yeah, the U in the middle, Chen, is exactly what I just said. It's the union. Maybe I wrote this a little small. It's the union. So we're saying it's like saying it's too small. It's like saying negative infinity to 2 and or including 5 to infinity. That's all that union symbol means. It's just a symbol to represent I'm including both intervals. So when you have more than one interval, that's usually what we use. We use the symbol of that big U to indicate that we're including both. Okay. Okay, so we've talked about quadratics, both the equations, factoring, using the quadratic formula. We've talked about the quadratic inequalities using test points. Great, so we're making much progress here. And just a few more things and then we're pretty much done. When do you use the upside down U? Saida, we use it when we have what's called an intersection. For the most part, in this class, we're not going to be using the upside down U as much. But it is good to know what that is. It's an intersection. So in this problem, we're not finding the common overlapping portion. So the intersection, when you talk about intervals, are the overlapping interval. But as you can tell, this interval here and this interval here have nothing in common. So we're not even saying what's the common overlapping region. We're just talking about what are the two regions that represent the solution. So we don't have to worry about that for now. Okay. Okay. So we're kind of jumping around a bit. So we talked about rational expressions at first, and then we talked about quadratics for a bit. And now we're going to be talking about circles. You're like, what? Yep. Talking about circles. And whenever I talk about circles, I always like to ask the same question. My question is, what is a circle? And a lot of students respond the same way. So I want to know, what do you guys think? What is a circle? Anybody? You guys can just answer freely. Don't worry. Yes, I know. That's the first question. Answer people say it's round. A shape without angles. Huh. It has no angles. I think you're trying to say something else. It has no vertices. Felipe, do you mean in math terms? I mean in any terms. It's just that math is so precise. It's the mathematical term, the mathematical definition is such a precise one. It's spherical. Well, spherical is in the 3D realm. We're talking about just the 2D realm, the two-dimensional space. Like, how would you explain it to somebody that has never heard of the word circle before? How would you explain something that's circle? So when you say round, right? The moment I do this, look, this is round too, right? Isn't this round? But is that a circle? And then people say curved, right? So that's curved. That's curved too, but is that a circle? And then the answer would be, well, it looks like an egg, yeah. An oval, sure. It has no corners, right? But this doesn't have any corners either, Saida. There's no corners to this. So is this a circle? So what I'm getting at is a lot of times we think we know, right, in our heads what we're talking about. But when we try to explain it, there's things that are missing. It's not the complete picture. So you start to see, oh wait, it's a curved shape. I drew a curved shape. But then you're like, no, but that's not a circle. But then I'm like, wait, but you told me it's a curved shape. So do you see how the things we have in our mind sometimes is an incomplete picture of what we really mean to say? So what are we missing with those answers that you're giving? It's an oval, it has no corners, it has no angles, an even shape. What are you really trying to say? But you haven't said it yet. That what makes a circle and not an oval, and not an ellipse, not a parabola? What makes a circle a circle? Radius, same diameter. So can you say that without using the word radius or diameter? So don't use terminology that's associated with the circles. Explain without using those words what those words represent. What is the radius? Yeah, but that the formula that's not that doesn't answer my question. What is the radius? I know you use that for the formulas and you find areas and circumference, right? But okay, so see, now we're getting to somewhere. The number from the middle to the top. What do you mean from the middle to the top? The same length all around. So that's something we want. It's the same length all around. Okay, the distance between the center point and closer. Yes, radius is like half the width of the width. Yeah, see, now we're getting somewhere, guys. You see this? The point from the center to any point on the, that's okay. See, now we're refining our definition. This is what we're trying to get at. You see? So it's more than just saying it's round. Very good. So you guys are getting there. You guys are getting there. And this is a good exercise, not just for this example, but for anything. You can always break it down as explicitly as possible. So what's a circle? A circle is the set of all points that are equidistant to a single point. That's a circle. It's a circle that if you take all the points that are the same distance to one single point, you would create a circle. And then you give these different phrases, you give them a word, right? You give them a label. So the single point that we're speaking of, we're going to call it the center of the circle. The equal distance that we speak of, we're going to call that the radius. And it's the set of all points, right? That's going to be considered the, as people have mentioned, the perimeter. So all you guys have been using the right words. It's just that I want to break those down, those words even further. So then when you start to think about that more closely, you start to see that, oh, that's why a circle is a circle, because all of these points here are of the same distance from the center, all of them. So then when you draw any line between the center and the exterior of the circle, the perimeter of the circle, that this distance is always the same, always. And we call that distance the radius. It doesn't matter if it's from the center to the top, from the center to the sides, the center to the down, so angled. It doesn't matter. All of these distances are always the same. We're going to call that distance the radius. And then we say, hey, what if we draw the line that connects one side of the circle to the other side of the circle, but that goes through the center? If you do that, you draw what's called the diameter. So this is the center of circle. So this is the center. This is the diameter. So let me move this around a bit. This is my diameter. I'm gonna call it D, and this is twice the radius. And this is my center right here. Center. Okay. Does that make sense? And there's a lot of benefit to understand why that circle is the way it is, why we define it that way, as the set of all points that are equidistant to a single point. And a lot of mathematics is expressed in words, but of course we use a lot of symbols to express those words, and we can create equations that express those words. So I'm just trying to make the connections for you guys that, like, I could have just done this. I could have just said, hey, you know what the equation of the circle is? It's this. It's x minus h squared plus y minus k squared equals r squared, and let's move on. Does it say on the left side equals? What does it say on the left side? D plus 2r? No. Oh, you guys can't see that? Sorry, I should make this a little bit more clear. I'm saying that this is the diameter, and the diameter is twice the radius. It's equals, yeah, not plus. The diameter is twice the radius. So you have one radius here, right? One radii, and then you have the other radii, double it. So what I'm saying is that this is the equation of the circle, right? And this is what I want you guys to know, especially when we talk about trigonometry. We're going to come back to this equation. But what I want you what I want to emphasize is that this equation of the circle is not just an equation that just exists for no reason. This here, believe it or not, this is exactly this. I'm going to say this again. This expression here, this equation, means exactly this. So a lot of the stuff that you see as formulas, right? You may just consider them formulas that I have to use and move on. But those formulas or these equations, they represent exactly they represent ideas, and these ideas are expressed in words. So you can express yourself in mathematics. Like the ideas that you may have, the words, the statements that you may have, there might be some way to express them mathematically. That's the cool thing. So this equation here is exactly saying that x and y are all the points whose distance from the center, and in the center is given by h comma k, that distance is always the same, r squared. So in this case, the center here is h comma k, those are the coordinates, and the radius is r. So if you find x and y that satisfies this equation, you would find the points on the circle. And all of them, all such x, y coordinates are the points that make up the circle. Okay? Not sure if that makes sense to you guys, but I hope it does. So associated with this, wow, that's bad. Rectangle here. Okay. So I guess I can say that this here is like this here is like the coordinate geometry definition. And this is the just the definition in words, right? Definition in words. And this is the like the pictorial definition, or the pictorial version of a circle. Okay, so we can express things in mathematics in words, in pictures, and in equations. Okay. Let me just see. So let me ask, find the equation of the circle with radius 5 and center 2 comma negative 1. So I want to find the equation. So what would be the equation of a circle whose radius is 5 and whose center is 2 comma negative 1? And again, we have the equation of the circle, x minus h squared plus y minus k squared equals r squared. So how can I use this information that I'm given to figure out the equation of the circle? So if the radius is 5, what do I have? I got r equals 5. If my center is 2 comma negative 1, then that means that my h value is what? 2, and my k value is what? Negative 1, right? And then the equation of the circle has the form x minus h squared plus y minus k squared equals r squared. So all I have to do is plug in the h, the k, and the r. So this will be x minus 2 squared plus y minus negative 1 squared equals 5 squared. But y minus negative 1 is y plus 1 squared. This is x minus 2 squared. And this is 25. Make sense? Yes. Okay. I'm glad. Straightforward. That's it. That's right. That's it. Chen. That's all it is. It's not nothing out of this world. But what if I get something a little bit more? What if I ask something like this though? Find an equation of circle that has points P 1 comma 8 and Q 5 comma negative 6 as the endpoints of the diameter. Now, what if I have something like this? Well, Chen, you want more steps? I think this will be the problem for you. So again, the same thing, the same question. What's the equation of the circle? But now I have 2 points, 1 comma 8 and 5 comma negative 6. These are the endpoints of the diameter. So if I were to sketch this out a bit, I would have 1, and this would be 1, 2, 3, 4, 5, 6, 7, 8. So I have this point here. I'm gonna call it P. And then the next point will be 1 comma 5 comma negative 6. So this will be, this is 1, this is 2, 3, 4, 5. And I got 1, 2, 3, 4, 5, 6, negative 6. So I got something like this. So I got P and Q, right? These are my endpoints of the diameter. And my diameter is just connecting these 2 points, P and Q. And they're saying that there's a circle whose diameter is PQ. So it would be like something like this, right? Of course, I can't draw that well, but let me see if I can make something happen here. Okay, great. So I'm trying to find the circle whose diameter is PQ. So what do I need? What would I need? I need 2 things, right? Right. I need to find the center. That's the first thing. So find center and find the radius. If I have the center and the radius, just like I did in this problem, right? Once I have the radius in the center, then I just have to plug in the equation of the circle and I'm good, I'm done. But now in this problem, you see, Chen, there's more steps. I don't have the center and I don't have the radius. They don't tell me that. I have to find it. So then the question would be, how do you find the center if I know the endpoints of the diameter? Divide by 2. What do you divide by 2? The endpoints. I think you're on the right track. You're on the right track. To find the center, you need to use the midpoint formula. Do you guys remember the midpoint formula? I think that's what you're meaning by divide by 2. So I want to use the midpoint formula. And the midpoint formula is x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So we're not just dividing by 2 for no reason. We're adding the x values. So in this case, it will be 1 plus 5 divided by 2. And it will be 8 plus negative 6, which is just 8 minus 6 over 2. So this will be 6 over 2, comma, 2 comma 2, which is 3 comma 1. So somewhere right here, right? So this is 3 comma 1. This is my center. Great. So I know, what do I know? I know that h equals 3, and I know that k equals 1. Okay. Now I found the center. So I'm gonna write that over here. 3 comma 1, which means that h equals 3 and k equals 1. Now, how do you find a radius? Does anybody know how I would find that distance? How do you find distance? Maybe let's start there. Does anyone remember the distance formula? That's for number 2. So to find a radius, you must use what's called the distance formula. What is the distance formula? D is equal to the square root of x minus x1 squared plus y minus y1 squared. Actually, yeah, it's x2 and y2. That's my distance formula. So if I have 2 points, I can find, if I have 2 points in the xy plane, I can find what the distance between it is by plugging it into this formula. So for example, whoa. So if I want to find the radius, right? I want to find the radius. Then that means I want to find, for example, the distance between P and the center. Or I can find the distance between Q and the center. It doesn't matter because it should be the same. So I'm going to use P, and P is 1 comma 8, and I'm going to use the center, which is 3 comma 1, right? So you can consider this as my x1, y1. This is my x2, y2, and then I'm going to plug it in. Plug it in the distance here. In this case, this would be the radius. So don't confuse this d with diameter. This is the distance, okay? Not the diameter. Distance. Not necessarily the diameter. It's not necessarily the diameter. So the radius will be the square root of x2, which is what? 3
Professor,
minus.
quick question.
Yes.
Could you have used the original other coordinate?
Which one?
5, negative 6.
Yes, of course.
Oh, you just chose to use the center instead?
No, I could have. So if you want to, are you asking me to use P and Q to find the distance between them? Like
Yeah,
this?
I'm saying, could you have used those 2 coordinates?
Correct. If you do though, if you were to do so, then you would find the
Have to divide by
diameter.
2?
You would have to divide by 2 at the end. That's right.
Okay.
So I am skipping that step by just finding P to the center first instead.
Okay, got it.
Or you could have done the center and Q and done the same thing. You get the same answer.
Okay.
But yeah, that's perfectly fine. So 3 minus 1 squared, and then you can say add then y2 would be what? 1 minus 8 squared. So this would be the square root of 2 squared plus negative 7 squared, which is 4 plus 49, which would equal the square root of 53. So that's the radius. The radius is the square root of 53. I found it. And so once I found the radius and I found h comma k, what would be the equation? I got it. The equation of the circle would be what? Would be x minus 3 squared plus y minus 1 squared equals the square root of 53 squared. But when you square something that's the square root, you cancel out the square root and the square. So then the final answer would be x minus 3 squared plus y minus 1 squared equals 53. Okay.